Hi, I'm Thomas Kindred from Wake Forest, and I'd like to tell you about smooth multisections of manifolds of arbitrary dimension. Start by talking about what a multisection is, focusing on an example, which is an odd dimensional sphere. For example, taking k equals 2, we've got S3, and this is the genus 1 Heegard splitting. More generally, an odd dimensional sphere is the boundary of a product of two disks, and writing it that way gives you this natural decomposition of the sphere into k pieces, and that is a multisection. And what makes it a multisection is that any setwise intersection between these pieces is nice in the sense that its dimension depends only on the number of pieces you're intersecting, and the dimension of its spine depends only on the number of pieces you're intersecting. Each time you intersect with another piece, the dimension goes down by 1, the dimension of the dimension of the spine goes up by 1. The second example, and if you want to look at this, I'll ask you to pause the video. This is an even dimensional example, similar construction, although here dealing with complex projective space using homogeneous coordinates. And again, the key property is that these setwise intersections, we can say what their dimension is and what the dimension of the spine is, depending only on how many pieces we're intersecting. And here's the definition. Again, it's a decomposition of your manifold into an appropriate number of pieces depending on the dimension of the manifold. All manifolds are assumed to be closed and orientable throughout. The pieces of the multisection, the xi's, all need to be one-handle bodies, meaning they have one-dimensional spine. And then we've got these two properties that the dimension and the dimension of the spine for the intersection depends only on how many things you're intersecting. Okay. Spine here, or dimension of the spine, having a spine of dimension, let's say 2, means that you have a handle decomposition using only 0, 1, and 2 handles. Okay, so some background. Every 3 manifold admits a Heegard splitting. Every 4 manifold admits a smooth trisection. Every 5 manifold admits a smooth trisection. So every smooth manifold up through dimension 5 admits a smooth multisection. And in fact, that in arbitrary dimension, every manifold admits a PL multisection. And the difference here between PL and smooth has to do with the definition of spine. But that's all I'm going to say about PL for this talk. Okay, what I want to tell you about is an obstruction to the existence of smooth multisections in even dimensional manifolds. And what this comes from is this theorem, which tells you that if you have a smooth multisection of an even dimensional manifold, then there's a handle decomposition of that manifold in which each piece contributes a specific type of handle. For example, if you have a 6 manifold, the theorem says that you can put a handle decomposition in which your first piece contributes the 0 and 1 handles, your second piece contributes the 2 handles, your third piece contributes the 4 handles, the last piece contributes the 5 and the 6 handles, and crucially, there are no 3 handles. There's an analogous statement like this for odd dimensions, but it doesn't lead to this type of obstruction. Okay, so how are we going to prove this? A couple technical results and then put it together. The first technical result says if you glue 2 manifolds together along some gluing region, and you know the dimensions of the spines of these things, then the dimension of the spine of the glued together thing is no worse than the 2 pieces you glued together or the gluing region plus 1. And then using that together with the definition of multisection, you can prove, among other things, that the union of the first I pieces, I plus 1 pieces rather, has a spine of dimension 2i. Okay, so now how does this prove the theorem? Well, we know x0 is a one-handle body, so it has a one-dimensional spine. We know x0 union x1 has a 2-dimensional spine, so when we glue x1 onto x0, we might need to use 0 and 1 handles and 2 handles, but we don't need anything more than that. And by similar reasoning, since x0 union x1 union x2 has a 4-dimensional spine, we don't need any 5 or 6 handles when we glue on x2. And now we get a handle decomposition for our whole manifold. We flip it upside down and use the same logic to narrow down the handles, and we get the conclusion that we want. And again, the point is there are no 3 handles, and so we're done.